So let's see the behavior of input impedance of series resonant circuit near resonant frequency, right? So series R, L, or C at resonance, right? So what is happening? But this is near resonant frequency, right? So G in is basically R plus J omega L minus J divided by 1 over omega C. And when this is happening, right, at resonant frequency, actually this is gone. This is subtract. So at resonance, actually, this is work as R. But what we are doing is the frequency is near the resonant frequency, so it's not exactly 0, right? At omega is omega 0 plus omega W, so this is very small value, right? So this will not be 0, maybe it will be small. So for this case, R plus J omega, this equation can be represented like this. Then omega is 1 over LC square root, right? So this R plus J omega L, 1 minus omega 0 square, and omega square. Because frequency is this, so R J omega L, omega square, and omega 0 square, omega square. So because we put this omega as this, frequency near the resonant frequency, so omega 0 plus omega square divided by omega 0 square can be omega minus omega 0 and omega plus omega 0, right? So this is delta omega, and this is 2 omega plus omega 0, right? Two omega minus delta omega. So this can be 2 times omega and delta omega and delta omega square, right? So this one is very small, so if we square, then we can neglect this term, very small, right? 0.01 and 0.001. If we root square, then it will be much smaller than delta omega. So using this term, this one, G in can be R plus, just approximate, J omega L, 2 omega and delta omega divided by omega square. So because omega, this term can be gone, so R plus J 2L delta omega, right? So for this circuit, right, this circuit at omega and omega 0 plus delta omega, in this case, G in can be seen as R plus J plus 2L, J times 2L and delta omega. So very small inductance can be shown. So if R is 0, which is lossless case, G in J 2L delta omega 2L omega minus omega 0, right? So let's put this as number 1, equation number 1. If R is not 0, it's because of for this series circuit, R should be go down for Q and omega 0 and L. And then L, if you make L in terms of Q, right, equation in terms of Q and R, you can make this equation, right? So if we plug this one here, G in is R plus J2 RQ divided by omega 0 delta omega. This is R. So R is here, right? So we can take out R and then 2 J to Q and delta omega divided by omega 0. So let's put number 2, right? So basically, we try to represent this G in terms of Q and omega delta, right? So we want to relate Q to G in. So we want to understand the relationship. So that's why we represent this G in terms of Q. So this is number 1 with lossless case. This is not lossless case. So let's consider the expression for G in of a lossless case, lossless series resonator. So G in is actually J to L omega and omega minus omega and omega minus omega 0. So this is a lossless case, but let's place omega 0 by omega, place omega 0 by omega 0 plus 1j divided by 2q. So this is a complex effective resonant frequency. So just kind of replace this one with this one, right? So if we plug in here again, then G in J to L omega and omega 0 minus J omega 0 and 2q, right? Then omega 0 L divided by q for the real term, and then so J to L times omega and omega minus omega 0, right? So basically Q is R, this one then become R, right? So this one is R plus J to L omega minus omega 0, and then L is from this one RQ divided by omega 0, right? So if we plug this one over here, then this term will be same as this term, right? Number 2 equation. So what does it mean? So from this kind of G in with assumption of R is 0, right? But with this kind of simple equation, if we change omega 0 to this term, complex one, then this G in will be same as this second equation, which means R is not a zero case, right? So this way, this is a very kind of useful method of determining the ZIN, right? ZIN. Finally, we determine GIN of a practical resonator. That means R is not zero case, right? So the effect of resonator loss can be accounted for by replacing omega 0 by omega 0 times 1 plus J divided by 2Q, right? So this kind of complex effective resonant frequency can be represented as with a Q, right? So if Q is very high, right? Q is infinite, then omega 0 and omega 0 are same, right? Because it's infinite. That means loss is very, very low. Loss is almost zero, right? But this Q is not that high, and this term will have some impact on omega 0, so that with this complex resonant frequency, we can get G in easily, right? So if we draw the input impedance of this series resonator, so at this, let's say this is omega divided by omega 0, this is G in magnitude, right? So when this is 1, so omega is omega 0, that means only R, right? Only R. Then this value will be increased as this frequency deviate from this omega 0 is 1, right? And then we define the bandwidth over here. So how we can define the bandwidth is actually for this circuit, RLC, so P in half of VI conjugate G in I square, right? V is GIN times I, right? And then this one can be G in V divided by G square, but this should be absolute value, right? So because this is complex number, so it cannot be divided each other. So if we only take a real part of this P in, right? R, right? G in become R and V GIN. So if GIN, so let's say when this GIN is R at W is omega 0, then power would be half of V square R, right? V square divided by R. But when this become 2R, then this power will be half, right? Half power. So the G in square is 2R. R means so this 2R means G in square should be 2R square, right? So the magnitude, so that this value become this, right? So if we take the point G in is because G in is root of R, right? So somewhat here root 2 times R. 2 times R, so root 2 times R. So if we take the point here, we can define that this is bandwidth. So power, real power into this circuit, series resonance circuit, become half. Then we call this frequency. This is bandwidth. So here 1 plus delta W divided by omega 0, delta omega divided by omega 0, and then this is minus delta omega and omega. Delta omega divided by omega 0, right? So basically bandwidth is 2 times, right, delta omega. So here is omega, delta omega, here's delta omega, right? So how can we connect this bandwidth to Q? So bandwidth, this is kind of so this is a absolute bandwidth. So a kind of frequency, right? So if omega is 10 radian per second, then bandwidth will be 20 radian per second, right? But bandwidth, this is a percentage. So omega divided by 2 delta omega, right? So this we call this is a percentage or fractional bandwidth, right? So if we define this percentage bandwidth in percentage or fractional bandwidth, then we can connect this with Q. So we learned that G in is J times R plus J times 2RQ and delta omega divided by omega 0, right? So we had this condition, 2R square. So 2R square is R plus Q delta omega. So R square is 1R plus. So this becomes a fractional frequency, right? So J RQ bandwidth square. So to be equated to R square and then R square, RQ square be W square. This is R, so that this bandwidth is 1 over Q, right? So bandwidth here is kind of fractional. So let's say I put just frequency, right? So if this performance is shown like this, G in, so let's say this is 10 gigahertz, right? And then this is R, and then root R become 9 gigahertz, 11 gigahertz, right? Then here bandwidth the definition is 10 gigahertz. This is frequency, right? So this is a 2 pi f right? So which is same frequency, right? So frequency, and then this is 2. Here is 2 gigahertz, right? So this is 0.2. So 0.2 using this bandwidth is inverse of bandwidth. So we can calculate like this, right? So this is bandwidth concept. So as Q is increases, right? Q is high, Q is very, very high, then bandwidth is very small. Alright, so that means this become very narrow, something like this. Something like this, right? This case. So when this is Q is very high, the response will be very narrow. But as Q is increased, Q is become smaller, response become broader, right? Bandwidth become broader. So I mentioned for the filter, right, something like this, frequency. And then this is a signal which is kind of passing, right? So for this case, it has a very high Q, but if we have some filter like this will have a Q is low. And for this case, Q is high. So this is a connection between bandwidth and Q.